Sometimes it helps to run the demonstration really slowly. So let me just review what we learned a little bit last time. And we're going to use it again today in some interesting mathematics as well. Here are the two masses, and you can see from the phasor that they're always separated by a phase of plus or minus 90 degrees in this case. This one right here is ahead in time of this one by exactly 90 degrees, and it maintains that perfectly throughout this resonance. So it started with nothing, this number 2 started with nothing, and now it's equal in amplitude almost to the driver. And what's different from what we did with a one-dimensional oscillator was that the driver was essentially infinite force, so it never lost anything. But here the driver is losing. It's coming down on the downside of its beat while this one is building up its beat, still maintaining 90 degrees ahead. This phasor right here is just in position to be able to draw the trajectory. Shrinking now, but still faithfully maintaining 90 degrees ahead. To its death of its amplitude, it will maintain that 90 degrees. And then it will go negative. And when it goes negative, it'll be 90 degrees behind this one. Okay, so now this is the driver, this is the receiver. We've just finished the big beat for this one. Now it's coming down in amplitude. This one went through 0 and is now building up. That's a day in the life of a resonance. And all of the perfect resonances, the ones that are really powerful from doing things, do this without fail. So it's an important thing to get used to. Now that 90 degrees showing up in a second component, that was an I that sat before the second component of the algebra that we talked about. And we'll be looking at that again later on. Okay, so that's an important piece of physics that this resonance business has, and of course with a simulation I don't have to worry about friction, but then usually nature at the quantum level doesn't worry about it either. The thing I want to do today is make a connection between the Schrodinger equation, the two-state time-dependent Schrodinger equation, and that old friend that we have, Newton's Newton-Hooke equation, Newton F equal ma, and then the F being the K matrix times X. So here we have a Hamiltonian matrix multiplying, and it will be a two-dimensional thing today. This is a two-state system, a two-quantum state system, and this is a 2 degrees of freedom classical system. So we're going to spend a good deal of time developing spinor arithmetic by looking at these two oscillators, basically two-dimensional oscillators. And we'll see the equations are virtually identical. And that's an important, I think, lesson that we can use for other things later on. It also makes symmetry analysis easier and a lot of things easier. So I'm going to back out of this animation right here, come back to the lecture and go forward. Now, most of the animations that we've been using or are going to use today are sitting right there for your use, and the parameter control panels and everything lets you virtually cover the parameter space for what we're doing here. And let's see what else I need to do. I also need to get this one in the play mode and remind you that that's what we're doing in the last lecture. Now, the other thing I want to point out about the eigenvalues, we spent a good deal of time doing the analysis of eigensolutions, and whenever we got an eigenvalue for the acceleration matrix, that was in fact a frequency squared. This is different from quantum mechanics. Quantum mechanics, the Schrodinger equation is first order, and the eigenvalues there are the energies, h bar omega, according to Planck's rule. So we're going to make that analogy more to the point. So here's the start of all of this mathematics that we're going to do that's in the center portion here, where we develop spinor methods, the methods that really Hamilton developed. This guy Hamilton's done so much. It's dizzying, in fact. But this development of first of all, what we call the Hamiltonian quantum mechanical world comes before he got to see the real invention of quantum mechanics. And let me get it up here on both screens, or all screens, in fact, all three of the active screens. And I want to show you how these two equations match under certain conditions and then under all conditions that involve a constant driver matrix like this. So we're going to be doing A, B, C, D physics. This is my mnemonic for a number of different ways to look at optical polarization, but any two-dimensional analysis is helped by this. I'll be always making connections with the old-fashioned notation while we're doing it. But here is where you would write a phasor, an amplitude. Okay, this is a complex number, not yet an operator. The next step is to quantize that. That's quantizing phase space of the oscillator of electromagnetism. That's called quantum field theory. Quantum electrodynamics begins with that step. But for now, it's just a complex number consisting of our old phasor variables, a coordinate for the first dimension and a momentum for the first dimension, x and p, number 1. And then the second dimension gets 1, 2. So there's two phasors that we were just looking at. Here they are in algebraic form, but in quantum mechanics that would be a psi 1 and a psi 2, or a chi 1 or a chi 2, and whatever favorite notation was used by mostly old-fashioned quantum books, but this is more up to date. Okay, now the other thing to notice this is that the H matrix, the Hamiltonian matrix, it has this requirement. If you're going to hold on to your probability, the sort of the currency of Schrodinger quantum mechanics is that the probability, that's the complex amplitude squared total, doesn't change. There's no leaks in your quantum system. You've accounted for all of the variables, all of the things that are going to change, and if it's a perfect quantum system, then the Hamiltonian has to be a Hermitian operator. That is, the off-diagonal JK or KJ are related by complex conjugation. If they're real, they're just equal. Okay? Well, we made some noise about how this matrix here has to be symmetric for reciprocity purposes. That's also, but all of this comes down to another axiom of time reversal symmetry. All right, let's see if there's anything I need to add to that. I guess not. So now what I want to do is separate the real and imaginary parts of the complex equation, that is the Hamiltonian quantum mechanical equation, and that's easily done. Let me make sure that this one has got that showing here as well. So we have a time derivative times I of this vector here, And notice, this is something that's very special about a two-state quantum system. It's not going to hold for a 3-state, 4-state, or 5-state, and that will make some changes in what we do when we go to do more dimensions. But most of the stuff that we're going to be doing here works in any number of dimensions. And in this case, what's interesting to note is you have exactly as many parameters allowed for the operator that's driving this thing as the state itself. There are 4 real variables here. There are 4 real, usually constants, but they can be turned into variables as well if you're careful. So it's 4 and 4, 4 matching 4. That's very special. 2 plus 2 is equal to 2 times 2. That doesn't happen with equal integers very often. Okay? Trivial case, 1 times 1 equal 1, right? But, not 1 plus 1 equal 1 times 1. So there's very special numerics going on here. Okay, so probably most textbooks you've written about quantum mechanics don't do this to the Schrodinger equation, and that is break it up into its phasor variables and just see what you get. And so that's what's going on here. I'm just literally writing out what this equation gives me, and you'll see eventually that it gives me the same equation that I get. If I separate the imaginary and real parts of this, I get first order differential equations for all 4 variables. And then we look at this one in detail and see that it can give you an equation of motion as well. Now, this is designed to give this result. This particular classical Hamiltonian now is what we're looking at there. And it is designed to get the result that I'm talking about here. Designed to get the result that gives you the same set of equations classically as quantum. So here is the velocity number 1, x dot, and that's the partial of h with respect to p1. And then for number 2 dimensions, same thing. But then I go and take the partial derivative of this with respect to p1, and I get this. You see a p1 showing up there, and there, and there, but not in the other terms. Okay, and so on. p1 dot is minus the partial derivative of the classical Hamiltonian, remember, with respect to the coordinate 1 and 2. Okay, so we go through this thing with those there. So this is totally classical physics right here. This is a classical Hamiltonian, a little bit more oomph to it than you're used to probably, and that oomph will show up later. But the main thing was designed to give this. That is possible is really important. So you see, these equations are identical. And that's what we're going to play with. We're going to play with the identity between those totally different subjects, classical mechanics and quantum. And of course, I don't think they're totally different, and I think you can see where I'm coming from. Okay? Now, to get the classical equations to second order, that good old K Hooke-Newton equation, I need the second derivative. So I go ahead and I calculate another time derivative here for this guy, and then this guy, and so forth. Okay, but for now, we'll do it down at the bottom, but for now, I want to get rid of that complex part right there. Okay, I'm just going to set that equal to 0. Okay, if I do that, then I do get Newton-Hooke. Okay, that's what's coming out here in this, and let me get the one down there to have that as well. So we end up there in the middle screen, and now finally this screen right here, for the C equal to 0, we've got lots of other parameters here that are not going to be 0, but here they are, and this is a symmetric real matrix with acceleration here and a position here. That's Newton-Hooke right there. Okay, so here's the double time derivative, and there's our K matrix with a minus sign that we put in order to make it stable. If you take that minus sign away, the oscillator hyperbolically blows up. But if it's a matrix that's particularly a symmetric one, and the question is this one symmetric? And it turns out to be yes. And so we at this point have a connection between these two very different systems. This thing here is giving us that. Okay. So I want to make sure we see that this right here, okay, is the second derivative. Now the basic idea is that I could skip all this. I could just do this. I could say I have a time derivative here for the Schrodinger. It's equal to this matrix, and that's supposed to act on your state. And I'm just going to square the thing. So I square this thing, and that gives me a minus sign here for a double derivative. And then I square the matrix, and I get this. So that's a shortcut to all this stuff here. Okay? A welcome shortcut. All right? Really welcome because I'd like to include C. So that's what I want to do next. Okay? So here it is. Without C, C is identically 0 by definition, and same thing down there. But now what I'd like to do, a little flourish here, this thing is very much showing you that the Schrodinger equation with the C equal to 0 is the square root of the Newton-Hooke equation. And that is the whole system. Take the square root of it and you've got yourself into quantum mechanics. That's kind of a weird way to say where quantum mechanics comes from. It's a trick, but it's a good trick. And furthermore, you can do it with C not 0. Okay. You can take this thing and square it and get that. And that's the equation we're going to be working with in order to make a comparison of a second order differential equation with good old Schrodinger, which is first order. Now I already have pointed out to you, I think, when we talked about the resonance curves, and there was the classical Lorentzian curves, real and imaginary part, right? And then if you made them really high quality, they started to look like the quantum Lorentzian, the thing that everyone calls, in this building, calls Lorentzian, okay? And that one had a lot more symmetry, its geometry was simpler, all kinds of things. That is the quantum propagator, okay? Coming a long way from the Newton-Hooke oscillator when you do that. Okay, I think if there are no questions, we're going to carry this forward. Let me make sure that I have on this screen, I'll put that final result. Okay, and same thing down here. Okay. All right, now, I think I shouldn't have jumped that far. Let me get back here. So the next step is, what I'd like to show you is the Hamilton-Pauli arithmetic, basically. It's Hamilton first, and then years later, I mean, this is 1843 that Hamilton discovers the quaternions. And we'll see what the quaternions are in just a minute here. They're nothing but spinors with an eye either taken off or attached, depending on how you look at it. So that's the connection that really is going to make this thing work. And what we need to do is get an exponential that goes, this is where I call the crazy thing theorem. We'll see that in a dozen or so slides later here. The basic idea is I want to take this matrix right here, and I could do all I wanted to do by simply spectrally decomposing it using a technology that we developed in the last lecture. But for this particular problem, this is far more elegant. It's quicker to do everything that we need to do. And I'm going to color scheme here for that, which I'll sort of explain right now. But the basic idea is I've got a matrix here that's got a 1, a 0, and 0 everywhere else, and I got one that's got the 1 down here. A and D stand for asymmetric diagonal. That is, if they're not equal, then it's asymmetric in the diagonal. So A and D, that's the mnemonic for these two matrices here. And then this is bilaterally symmetric. That an object that that has this is going to be like our pendulums with equal masses and equal springs. And then this is the crazy one, okay, the C. Okay, the C, what is the C? Well, it's got a lot of things that begin with C. Chiral, it's got handedness, it's going to make circular polarization. It's a complex component of this, the only complex component of this set of equations. And it describes Coriolis effects, it describes the cyclotron effects. It has a curly field. It's quantum mechanics where you have current carrying going on. Okay, so C. There are lots of things that make us want to call this C. Okay, and B is pretty good too. Asymmetric dot. So that's what we're working with here. Now, if you don't turn on that C, then this is what we'll be working with. This will be what asymmetric diagonal looks like. That is, it has a fast axis and a slow axis for oscillation. They happen to be on the Cartesian coordinates, so there's no coupling between x1 and x2 for this one. It's got zeros off diagonal. But if you turn the off diagonal on, okay, but still leave these unequal to each other, then this ellipse will rotate. We've seen that geometry of the ellipse rotating as you go to off diagonal quadratic form, right? And finally, if you make the two equal in the center there, it locks in on the 45-degree line, and that's what we call B symmetry. So if you don't get this guy involved, the crazy one, that's the other thing that's C, right? Right? If you don't go for crazy, these are this and this really. I do half sum and difference to make the coefficient of the Pauli matrices. This is Pauli matrix number Z, the third of Pauli's. It's our first. Okay, this guy right in the middle here is our second, but it's his first. This is X. This is sigma X. Okay, and then this crazy guy right here is sigma Y. Right? Remember that from your quantum mechanics. Okay, and then of course there's sigma 0 or sigma 1, whatever you want to call the unit operator. So there's our four-dimensional system. This is a four-dimensional hyper-complex system. It's got enough dimensions to take care of relativity. X, Y, Z, and T. That we won't go into too much here. That's coming, if you want to take our group theory course and stuff like that, you can see a lot of that. But right now, we definitely have four things here that play the role of the thing. So let's go ahead here and point out where the history of this came in. I'll go ahead and just jump to most of the history and finally a final line there. So let's just speed things up a little bit here. But the basic idea is that the Polyspin operators, and here I'm telling you B is X, C is Y, and A is Z, make a connection with our little coloring that we do, and 1, 0, that's pretty trivial. But Pauli comes in 1927 in this particular paper with the help of Jordan and a few other people, and they're way behind Hamilton. 1843, he's got these things called I, J, and K, and 1. All right, that obey a certain arithmetic. Basically, he was looking for hypernumbers that behave like the imaginary number I. So the first one is called I, but fat I, because it's got a matrix behind it, and then J, fat J, and fat K. Well, these all square to -1, just like the imaginary number. Okay? But altogether they make up what's called a quaternion group. It's a group of order 8 because you don't count I and minus I as the same element. Okay, anything else I need to say about that? I think that I go ahead and say that what you get out of the 1 and the sigma A or the sigma B and sigma C is a cyclic group of order 2. You have the A group, the B group, and the C group. The unit doesn't, that's a C1, but the C2, that's bilateral in some kind of symmetry. the sigmas all square to plus 1. So all they are, you see, is the quaternions multiplied by minus I. I'm writing it the other way. I'm saying the fat I is the good old square root of minus 1 plus I times sigma b. And then sigma c and sigma a, they play the same role. So the quaternions here are being written in terms of Polyspinors. We're going to be very quickly here doing the opposite. We're going to be putting i's on quaternions in order to make them into Polyspinors and square up to plus 1, not minus 1. That turns out to be slightly more convenient for arithmetic. So most people don't even know that Hamilton developed the spinors. You know, it's one of those things where he was so excited to get something that was generalizing complex numbers, and that big deal by Euler was really a big deal. To be able to do all that stuff we did in chapter 10 of unit 1, right? That's pretty powerful. Okay, so you have to be aware that he's being very excited when he discovers three things that make a hypercomplex number system. So that's what we're after here. And I might as well get to the bottom line of this right now. And that is, our objective is to evaluate the solution to Schrodinger equation. And that's the solution, except that I've got to know how to take an exponential of the Hamiltonian. So what we need to do is convert this exponential to a 2-by-2 matrix. That's all we're going to do for the next almost a dozen slides. Okay? But in the process, I want to go through and make various pieces of the thing that we're going to be needing to use when we do get this thing reduced to a 2-by-2 matrix that we can easily write down for any of the parameters A, B, C, D. So, the symmetry relations that we're talking about here, as I say, make these things square up to 1, unlike the quaternions. Okay, there's an example of all the products that we would be getting if we were to look at this as a linear combination, like I'm doing right here. The idea is that sigma x squares up to 1, sigma y squares up to 1, and sigma z squares up to 1. But is that the only ones that square up to 1? Turns out there's a continuous infinity of sigmas that square up to 1. You are able to take any vector with 3 numbers that squares, that is, has a magnitude of 1, and then make something called sigma, not just sub x, but sub any vector, any unit vector, a component in any direction. Okay, that's what this notation is I'm mentioning the Gibbs Dot Product in effect here, and I'm using these 3 numbers here to multiply that. And they're real numbers for now, and they are going to give us this collection of 9 terms. That is, if I square this thing to see what its square does in comparison to just the squares of each of these sigmas, well, is it any different? And the answer is no, it isn't. And the reason it's not different is because of the multiplicative properties of those Polyspinors, which are as shown there, and there, and there. Okay. So, one thing that is screwy about spinors is they anti-commute. That is, sigma z times sigma x gives you something that looks like it's going to be a sigma y. It would be if I just take an I away from it, so that I get good old, it's curly here. And so that's one multiplication. Z times x gives you I times y. But flip them around, so you do z first and then x, and I like to say that because usually I operate with things like this on the right. So this gets to x first and that gets to x second, and then I have reversal of this, and that's just a minus of this. So the anti-symmetry of that kills all the cross terms in this expression right here. you see here, minus x cancels plus x, and so forth down the line here. Anything off the line. And then we already said that ax squared and ay squared and az squared, they were all equal to 1. This was a unit, taking a unit vector here for this thing. And the result then is that sigma a squared equals 1, just like all of the others. So there's continuous infinity of these things. Pick your components by pointing a unit vector in some direction. Okay, that's cool. That's really important. And of course that's what Hamilton apparently, and I can't read his mind, but that's apparently what he was realizing when he was so excited. He carved the multiplication table of the quaternions into a wooden bridge, which sat there for years and years. And now Daniel Kennefict has told me that the whole thing has been carted to a museum and polished up so that you can actually read it. Anyway, it's really a big step in mathematics, bigger than Euler's step that started the complex numbers. Now here I'm doing just a little bit differently what I just completed here. Here I'm going to go ahead and look at some of the products of x with y, x with z, and so forth. And we're going to show that you get not just a dot product of interest, but also cross product of interest. So here I'm going to do sigma a times a different sigma. So here are two different vectors. Okay, and then we're going to multiply those out and get 9 terms. Okay, now we need to know these products really for sure. Here are the products written one way, here they're being shown in a matrix proof of that. And what I'm ending up with here, and this is just what's really cool about this, is now we take these off-diagonal guys and put them over here, and look what you get. This is what I think is a very cool identity. And without it, we're not going anywhere today. Okay. Now, this is where Gibbs got his I, J, and K. He left this country to go to where they were smarter and learn what the Germans, the English, and especially the Irish, Hamilton is involved in this, and he learned about the quaternions, and he decided, hey, you know, that has, and he had already invented something called the cross product, and that's what we're getting here. So, you know, you've got to give him credit, and what he has to do is dumb it down so that you can bring it back to those Americans, right? And so the vector calculus that you see in every course now has I, J's, and K's, and the identities that come from this. Now we've already gone the other way, right? Remember when I asked you to do the A star B product, or think about it, right? That means a conjugate of A times B. That's this thing with a minus sign there, and then the B just by itself, okay? And together you get the dot product for the real part, and then the imaginary part is one of the cross product components, namely the components perpendicular to the complex plane. Well, he's getting all three. And this is the original I right here, but he's getting X, Y, and Z components of the cross product. Apparently this was also in his head as something that was really cool, that made this work. He had the algebra, he'd been thinking about the algebra so long, and then suddenly he realized that he could make something out of it. But he didn't write this one on the bridge. And it would have been sort of funny if he had an X, Y, and Z all of a sudden, but didn't. Now, the next step on this is to look at the series that comes from what we've already done here. So that, after we get this thing up to speed here, what I'm doing here is just going through and looking at what happens when I do the complex e to the minus I phi, which we talked about so much in Unit 1, Chapter 10. So here is a series, And half of them are real, half of them are imaginary, right? But the basic idea of this is that as you take the 0th power of, let's use minus I, because that's what we're going to be using polyspinors, and we've got that minus attached to them for quaternion purposes. The minus I to the 0th power is 1. Then first power of minus I is minus I. Second power is minus 1. Third power is plus I. Fourth power, you're back home again. So this, the quaternion group 4 really means something here. You go through 4 things and you start over. Well, the Paulis do the same thing, you see. The Pauli matrices do exactly the same sort of cyclic behavior. After you've gone past 4, you start over again. So if I take a minus I sigma, any component, I can pick any component for this thing. Again, that's an important point. But the 0th power, the 1 power, the 2 point, they're distinct, and then you start over again, just like you do here. So that means you can do an exponential with this crazy thing. And this is the crazy thing that we're going to be talking about here. So right here is where you make a solution to this. This is now being done. Okay, let's put a stamp at a big done on this particular step right here. Here's the old guy, here's the new guy in Dublin. A full one. I've made this now into a 2x2 matrix because I know what these matrices are. Right? And I know the unit matrix, of course. So I've kind of, to honor this thing in an American way, I call it the crazy thing theorem. That is, if you have a crazy thing that squares up to minus what you call a unit, then exponential of the crazy thing times any parameter, these imaginary parameter, complex ones too, is your unit times the cosine plus crazy thing times sine. That's the crazy thing theorem. Isn't that cool? And it's not so crazy. Crazy like Fox. Okay? So I make a big deal about this. Already here with minus I, okay, the crazy thing is minus the square root of minus 1. And I don't have to use minus. Plus is also a crazy thing, and it would apply, but the squares of either one comes out to minus 1, all right? This is the really crazy thing here that we're taking from Hamilton's way of looking at things. Okay, I'm going to leave it there and make sure you've seen all of this and it makes some sense. Okay, so this is what we're going to use to solve Schrodinger equation as well as the oscillator equation in a weird kind of way that lets us do optical polarization. For example. Okay, well, we need to show that this thing is a rotation operator in some kind of weird space. That's the first order of business. And then we discovered, because of one space is kind of the square root of the other space, or vice versa, square of the other space, okay, we're going to get a factor of 2 in a lot of places. And they're important factors of 2. Failure to take cognizance of them will definitely lead to disaster, mathematically speaking. And so we need to do that, and we'll come on down and we'll be making the NMR Hamiltonian. I hope to demonstrate that with a magnet here, but that let's get the algebra done first. So this is done now, and we're talking about writing various crazy things into this equation here. This crazy thing in particular, okay, this is a three-dimensional crazy thing. It's some vector in a real three-dimensional space, and then this is just a one unit operator, but these things are 2x2 matrices that we've been looking at. Let's look at the easiest one first. Let's just see if I can take the exponential of this 1 minus 1 diagonal matrix. And I don't need the spectral decomposition stuff that we talked about last time to check this. I'm just going to plug it in here, right here. Okay, minus I times, and this is our sigma AD, sigma A, is, I just call it sigma A, forget the D, okay? And that's going to be multiplying that minus I times that matrix is going to be multiplying the sine according to the crazy thing theorem, and then this thing will be multiplying cosine of that parameter that is going right there. Okay. Well, here's what you get. I get a minus I sine here. I get a cosine of phi, and again a minus there. And let me see. I see them as something is this is a plus sign. Actually, minus times a minus is plus. Make a note. I think I actually changed this back from being wrong to right and then back to wrong again. Anyway, it gives you what you'd expect if you just think about the fact that you've got a diagonal matrix here and you've got eigenvalues, and so you just get that. That's really simple. Okay, so let's get that on all the screens here and then go to the next step. I want to do sigma C, the crazy one. Let's go after the crazy one for first. The chiral, Coriolis, you name it, complex component that gives us that. Okay, and here it is right here. Okay, so now we have something that's anti-symmetric, off-diagonal. Okay, and all I'd have to do is take that crazy thing, stick it right there, minus I times anti-symmetric off-diagonal, put a sign on it, then the cosine goes with the unit again. I think you recognize this matrix immediately as a plain old two-dimensional real rotation, right? Okay, well, that's encouraging. That's something to, of course, I would guess that Hamilton did that first while he was playing with these things. But let's just do the whole thing. Okay, this is really done here. Okay, now we're really done. We're going to do it for all possibilities, all possible three components that sit making the combinations A, B, and C. So this is what you get. You go ahead and just take a general crank vector that's pointing in any direction, and this is the representation that it's going to give. And I'm writing that in two different places here. Basically what I'm saying is this is a polar Cartesian layout, in this case of the unit one of these things. That's this thing with a hat on it that indicates that this vector had better be a unit, real, three-dimensional vector. Okay? And here are the components, A minus D, for asymmetric diagonal, what we just call it A for short when we're using indices, and then B for bilaterally symmetric, and C for that curly Coriolis centrifugal complex current carrying operator, the real weirdo in this gang here. Okay, so if there's anything else I need to say, there is the 2x2 matrix. You simply have to substitute in whatever this gives you for the unit components. That is a unit polar vector. Now remember, we put the Z, what they used to call Z, first. And then the thing we call B, bilaterally symmetric, that's second for us. It's first for Pally, right? And then this last guy right here, that's the C. That goes where we would normally put a Z, so it's kind of our Z. And then this one has to be divided by the square root of the sum of those three components. This component squared plus this component squared plus this component squared. Those are the actual components that are indicated. Here they are before they've been unitized, and here they are unitized. Okay. All right, so we've got all we need to do the mathematics that's coming. Now, one of the things that you always do when you get new operators, and I'm sure Hamilton probably did this first, is you make them rotate each other. This thing is going to be doing rotations, like that one's very obviously a rotation in the two-dimensional space, which is going to be in 3 dimensions. we got to somehow get these the real vector space, the real world, the world that we think we live in, which is three-dimensional real, married up, or at least talking to, without swearing, the complex two-dimensional world that matrix, and I haven't written down the x component of that one. It's pretty much the same thing with I sitting on the signs. That needs to be looked at carefully. So the next thing that we do here is we imagine rotating sigma A, which is this nice, shall we say, civilized diagonal matrix, and I'm going to use that C matrix. Here it is, and here's its inverse. But what I need to do is hit it twice with that in order to rotate it. And that's the factor of 2 that's going to creep into all of this. But the basic idea is that I take the matrix that we just wrote here, operate, and that works on the bra side of this operator. And then the ket side, it's got to be hit from this side by the transpose conjugate, but actually the inverse is all you need in this particular case. So put those all together. Looks like a mess at first, but then trigonometry says, oh no, you just got a bunch of double angle cosine and sine here, and that's going to be what this rotation does to a sigma A. Now I notice things are a little bit out of kilter on that one, but still readable. And the one down here, I hope, is more readable, more like this one. I don't know what happened right there. But in any case, what we've just done is we imagine that this guy right here is some kind of rotation around the c-axis, okay? And it's going to take the x guy and rotate it over to a linear combination with twice the angle of the original A-type thing, the thing that Pauli calls Z, and the X part of the thing that Pauli calls X, that we call B. So A and B are sort of rotating into each other, and then we go ahead and we apply the same operation to the B as well. So the effect of applying this green, see here, and let me remind you also there's a color scheme to this. The A and the B are kind of red and orange, are traffic light that means stop, right? And C is just go. Okay, so you see that green anywhere, that's the one that makes things go. These guys make standing waves. This guy makes moving waves. That's really what it boils down to. Okay, so the coloring is intentional here and has deep physical connotations for symmetry. So, and once again, here's the unit of phi vector. It's the phi vector divided by the sums of squares of those components, A, B, C. And also the other thing that we're going to be doing here is we're going to be looking for an omega, the frequency. But frequency times time is angle. And so all of these phis here are actual angles rotated. And this machine here is going to help us visualize that. But let's not get too far ahead here. Okay, any further questions about this? It's worthwhile seeing what it looks like if you continue and work on the B with the C. Okay, very similar trigonometry. The B was sitting right here in the horizontal plane with the C, and it gets taken down here by the same double angle, the sine and cosine of 2 times whatever I've put on the rotation C. So here's what the green does. It rotates. But that's what the other ones do too, as you'll see it when you work some of the problems that goes with this. Okay. Let me get it in the center screen here first. So this is the use of this stuff for just doing rotations, and that's what we're going to show, is that in the three-dimensional space it has A, B, and C. That's what we usually call X, Y, Z permuted. the oscillations in two-dimensional complex space become rotations in the spin space. And that's what we're going to spend the rest of the showing examples of and explaining. Okay, so the geometry of evolution, really revolution, rotation, operator, okay, first of all has these mysterious factors of 2 that we see first right here. But it would really help probably to pause for a minute and just collect all of the algebraic quantities that we're dealing with here and separate the way we deal with them if you're working in that complex 2D spinor space. And that's what's shown at the top here. Just what we started with. We take this Hamiltonian and break it down with these lowercase omega coefficients, and they're Cartesian components of rotations for that space. And then the sigmas and the A, B, and C are here, and there's always this unit guy to take care of the overall phase of a quantum mechanical system. And this is the overall notation that we write when we make them fat, as though they were three-dimensional vectors. But they're always four-dimensional quantities. They can do relativity as easily as they can do just plain rotations in real three-dimensional space. So anyway, remind you, red for stop, asymmetric diagonal. Bilaterally balanced, it's got symmetry that prevents currents from happening. And the combination of those two, same deal. This is the one that makes things move. All right. Now here's the notation for 3D vector space. Same stuff. This is equal to this. Okay. This matrix can be written this way if you're going to play with spinners. Be written this way if you're going to look at the three-dimensional vector space, the real world, what we call the real world, not that stuff that's behind the scenes that makes us have our spins, our spin a half a quanta. That's got to be explained, okay? At least as far as we can. But what we do here is we switch this 1/2 factor here to the matrix. And then this one right here, we do the same thing. We put a half in here, but we put 2 on this one. And the C the same way. This one's got this A minus D over 2, half difference, to go with a half sum. So these two guys kind of play with each other in a diagonal system, a trivial system. Okay? But these are the ones that put the guts on us. So we've got this asymmetric diagonal, bilateral balanced, and C, 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 okay, as our thing. And look what we've done. We've got here what are the angular momentum operators. These guys, Polyspin operators, and let's get everything up to date here. The S's are Jordan angular momentum operators for quantum mechanics, and J is often the label used in respect of Jordan, who was really the mathematical brains behind the Pauli experiments. Now, I tend to think that Jordan probably just went and looked up Hamilton, right? And came into Pauli's office and said, hey, here's the way you do it. But anyway, whatever. They're called Pauli spinners now, not Jordan spinners. And, you know, somehow people lose the historical imprimatur that they maybe deserve. Okay. So these guys with a half quanta, that's what it ends up having, are the ones that we're going to be working with when we look at this thing in 3 dimensions. Meanwhile, these guys up here, you see, don't have that half in them. They square up to 1. This thing, well, all 3 of them squares up to 3/4. That's the total angular momentum squared for spin a half. We'll get to that later on. Okay, so when you want to do the rotations, when you want to do e to the minus I Hamiltonian, which is the propagator for this system, okay, you're doing this exponential here. We already know how to do that. We write it all out in the crazy thing expansion. Okay. Well, we use different notation for that too. That's good enough for doing the spinor space, but when it comes time to do this, let's go ahead and put all of that on both of these sideboards. Okay. So now, what we're going to call our angle, our actual turning angle in three-dimensional space, and let me show you where that is. It's right here. Okay. That's the operator. It's going to rotate the spinner. The spinner's in there. Imagine a little vector, spin vector inside there. But this is doing spinner arithmetic. And in general, it could be at any angle. You see, I can rotate this thing around in the azimuth. That's called italic phi. And then this is italic theta that is on this dial right here. Okay, so those are the main angles. But then you got to turn it some. And this can be called lowercase omega. I could put that on this one, but it's uppercase omega when you're in 3 space. That's what this is. The little omega up here becomes uppercase. They are related by factor 2 or 1/2, depending on which way. This is the bigger one. And you see its multiplying angular momentum is the smaller one. So this is exactly equal to that. They just trade half factors, or trade 2 factors, depending which way you're going, right? Okay, so this puts them side by side. The stuff that we work with when we're dealing with the space we live in, and the stuff that's going on behind the scenes that has really got all the truth. This loses some stuff. Some stuff we can't see. The phase part is really hard to see. Okay. All right, anything else that we need to say here? This is just exploring the 2 crank vectors for this system of equations that work in the different worlds. And we need to make pictures of those different worlds side by side in order to really make sense of this algebra that we're doing here. So this is a case where I'm really doing the geometry last. You can do it a lot quicker if you go first, but then what the heck are you doing, see? So there's pedagogical boundaries to our way of explaining this stuff. So we'll go ahead here and just really show one thing about the factor of 2 that comes up when we go from spinor world to vector world. This, I think, pretty well clarifies it in a way, but it still leaves a lot of mystery. The basic idea is here, I am living here in spin up, spin down space, which you're used to doing in almost any modern quantum mechanics book, right? And meanwhile, over in the real space, there are the x, y, and z components of a spin vector. Uppercase x and y and z. Make everything big for this. This is the big one. One has big rotations. This one rotation here is twice what this one has got. And you can see why that is, because remember, our rotation matrix that we got had a half in it, right? And you need to respect that. So we're talking about going from spin up, okay? We rotate the thing around, okay? This is spin up right here. We rotate the thing around, right hand rule for this particular matrix. So I gotta use my right hand on this one, okay? But I'm only gonna go pi over 6. This one goes pi over 3. Pi over 3, okay, 60 degrees from the top. And this one goes just 30 degrees from the initial, the sides spin up state. Okay, so when this one has gone, you see, 180 degrees, that's spin down, right? So is this one, because spin down is only 90 degrees from spin up. That's the problem right there. You're calling this up, or this one down, this is up, that's down, right? Not in that space. Down is down and up is up. It's only halfway here. So we still got one more full rotation here, 180 degree rotation to complete this. But that's what is going on here is I go from spin down here around some more. Okay, and these are all new states. We haven't seen these before. We have seen those. We're just covering it again on this side of the three-dimensional world. We're covering it again, right? Where this one finally, okay, here has gotten over to here, okay? And this is nothing but minus spin up. This seems crazy. What looked like a full rotation of this thing, but I got something that's out of phase. And that's precisely what we're going to see in the oscillator animations that are coming. You will see that when you go bouncing through that Lissajous pattern and actually go far enough to come back, it won't come back, it'll be on the other side, it'll be minus phase. So this sounds crazy, but the geometry of this thing demands what we're saying here. So I like to say it, life in the 2D spinner space is half fast. Okay, like some of the administrators around this place. Anyway, the full angle, 4 pi, 720, is needed to return to the original state. That's how much of a rotation in 3 space you've got to do to complete that. Now, let me go ahead and make some physics here and maybe even actually show you a precessing spin due to a C-type Hamiltonian. But here is a very simple Hamiltonian for a quantum system. The quantum system lets you do MRI, magnetic resonance imaging. It used to be called NMR for nuclear magnetic resonance, but everybody's afraid of the word nuclear, so they got rid of that. So it's now MRI, right? You won't find the word nuclear anywhere in hospital, right? Even when you're using radioisotopes, they won't tell you that. So M dot B, magnetic moment, that's G factor times a sigma operator dot B. And B is a vector that has X, Y, and Z components exactly where they should be according to the stuff that we've built so far. So this is a notation of the 2D spinner space, so actually 2D spin space, but this is the spinner combination right there. Okay, so this particular guy is just called Z, but we call it A, or AD, bilateral balance, B, and C Curly complex. Those are all possible components for this object. And go ahead and advance this one to the actual picture of what I'm imagining here. Just to make connection with the physics that is behind all of this stuff. And this NMR, nuclear magnetic resonance, is a paper by 3 authors, Rabi, Ramsey, and Schwinger. And what an amazing thing they were discovering was that as we stand here in the magnetic field of the Earth, say it's going right there, all of our water molecules have hydrogen spins that are spinning around that. So we have little tops in us that are all spinning like crazy just because of the magnetic field. Right? I mean, that's the way they put it. Now, later on, Feynman, Vernon, and Hellworth, just a year later, come out with a paper in which they more or less generalize the use of the polyspinners so that they could say, hey, this will work for a 2-state atom atomic system or any 2-state system. Okay, so it's kind of funny that all of the work that the Americans did on 2-state systems required 3 Americans. Now, I'm tempted to go ahead and play some of the animations. We know they're going to work, but not necessarily going to work is this little gadget right here. What I've got here is an air bearing, which we'll use later for some mechanics. It's more complicated than what we've got. But what we have here is a little sphere that's got a it's a neodymium magnet pretty strong magnet in it, and I had a pencil here that was very sharp, and it probably so sharp it went through the floor to the next world down. So I'm going to make another sharp pencil right here, and then I'm going to stick it on this thing and get it rotating. Okay, and I've got to be a little bit careful with it. I've got to find the hole. There we go. Okay, so I'm going to spin this up, and then I hope to be able to rotate that. Let's see what happens if I, there we go. I turn up a magnetic field. That's what this is. Give it a little bit more thing. I did it sort of like, so it's a little bit of transience. You see the thing processing. Okay? So there you are. Very crude demonstration of this wonderful discovery Robbie Schringer made. Okay, and it's so important because now we do medicine much better than MRIs, right? Okay, so doing that, of course, is a long way from just spinning this thing around or doing that simple absorption experiments that they were doing. But nevertheless, I wanted you to see that. Now, the omega vector that's there, that's the actual field. That's the field, that's these components right here, dotting the little omega with sigma. This is in the sigma world, but in the other world, of course, they're twice that. Okay, now let's just take a picture that is available to you, and we're trying to make this a computer picture as well. That's going to take some doing. All the new technology now for virtual reality is starting to pay off, and we can actually fix it. So you own one of these things. There's, as far as I can tell right now, 2 of these in the world. I built it for a Reviews of Modern Physics paper that I wrote. I didn't build it. I just drew a crappy picture of it. And then the guy at Jill, I was at Jill at the time, and he was a really incredible machinist. He's an instrument maker. And they needed that because they were doing world-class resonances and all kinds of things. And he said, I want to make that. And so he went and got all the junk from all the other experiments and started machining them down. So he had one, and the way he made it is the way my picture was. It had a ring all the way around here and then a ring all the way around there, and completely made it so you couldn't do the 2 pi, 4 pi experiment with it. This one you can do. I built this one at Georgia Tech with the help of an ordinary machinist, where I had to draw the 3D drawings, and then some of the things I had to machine myself. And that was good practice for running a mill and a lathe. But anyway, basic idea is that the Euler angles that you see in every textbook, they almost always are pictured exactly like that, is an astronomer's diagram. Because what the astronomer is interested in is when something that's in an orbit around the sky rises from the horizon. So they measure things off of the horizon. Everything has to do with an angle on the horizon and things like that. Making a diagram that has frustrated, I don't know how many physicists and perhaps mathematicians too. But anyway, the Euler angles are very obvious when you see this device right here. In fact, it's written alpha on this one. And let me go ahead on this screen here and show what we're going to do with that, as well as a picture, a sketch of this with everything labeled. So maybe we look at that first and then we'll come back. The idea is there are 2 coordinate systems here. The coordinate system of the laboratory, obvious, and then the coordinate system associated with this ball here that has axes that I indicate with little bars over them. For example, the z-bar axis is right there, that orange vector, okay? And then the other 2 axes are hiding more or less. There's the second body axis right there. There's the first one labeled right there. Then there are these frames that connect this to that. This guy right here is called the X prime frame. It's really a frame. It's an aluminum frame. And then there's an X double prime frame. Okay, that's the one that's inside that one right there. It's dialing off of that one, whereas this one is dialing off of the azimuth. And these 2 coordinate systems essentially share this dial, the beta dial, but this one's got its own azimuth to match this one's azimuth. So this makes a very clear description, which is essential for doing modern group theory, in my opinion, and that is that there are two worlds. There's the world associated with this laboratory, and then there's, relative to that, a world associated with whatever it is you're working with, molecule, nucleus, photon beam, you name it. So that's why I built this thing, is just to be able to understand the spaces better. But now it's possible for us to kind of do some experiments. But first of all, basically defining Euler angles as matrix objects. That's really the key thing here. And the idea is, in order to set the Euler angles, how do you set the Euler angles? You start off with the thing lined up where all of the dials read 0. Now you can't see that from where you're sitting, but I know they are because I'm right on the y-axis. Now that's our c-axis right there, so that's the curly axis, the one to work with. And the first thing I do is I set the alpha dial while I still can with just using a Z crank. I set the alpha dial first by just putting the thing there and setting whatever, say 45, 60 something degrees, okay, and hoping it stays there. I should probably put some Scotch tape or something to keep it there. And then the second thing I get to do, because it's still pointing at me, is the beta dial. I set that one, and that's a right-handed positive, so I have a positive angle reading there right now. And then the last thing I do, and I'll always be able to change this one because it's my azimuth in the laboratory, I put the thing on there and set the alpha. Follow that? This is first, because we tend to operate on things that are over here, right? So this gets to act first, then this one, then this one. Okay? That's what happened here. Now, what happens in the algebra is shown up there. Okay? And here. That's the actual matrix algebra right there. And that's what you're seeing there. So, having done that, I get a big 3x3 matrix with terms as components that I'm really sure of. This really gives me confidence in the resulting 3x3 matrix. But it also gives me the components of these vectors, z bar, y bar, and x bar of the new system. The z bar is an easy one. It's the polar coordinates, and alpha for azimuth, that's the alpha dial at the very bottom there. Then beta for the polar angle, rhymes with theta, the usual letter that you use for this. We reserve the theta for operators, not states. This is a state vector describing just the point of the what will be the spin vector of our spin analysis. And then these are the side components right here, and that's cool. That's an easy way to understand rotations. Now you'll notice there's body frame coordinates for this. This is what the people in the body frame would say your laboratory was doing. Little minus signs. There's two minus signs there, so that's the same, but same idea. Okay, so that I think is important, and there's the picture of the bod frame versus the lab frame. Okay, just to sort of get you used to living in the space that the molecule lives in, or whatever it is that your photon beam or crazy thing that you imagine doing physics with. Okay, so what we need to do is this same ordering: gamma first, beta second, and alpha last, for an actual spin state. That is a state that's spin up. So I draw this ball here and then imagine a big S vector sticking out of this part here, you see, and that's what we're going to hope we can make down in the shop. We make a classic, a clear plastic sphere and have a vector inside that to really make it clear. That's the S vector, but it's got more components in order to keep track of the U2 space. That's what this is, unitary 2, quantum mechanical bispinor state, well, two-dimensional space. And when you put all of those together, you get the most general, and let me just get this on all three screens because this is really important for what we're going to be doing here. See if I've got that. This looks like I've jumped ahead just a little bit here. No, that's fine. So this is the spinor space that we started this lecture with, x1, p1, x2, p2, or a1 and a2. So this is giving us the polar coordinates of that. And one of those coordinates, the gamma, that's this guy right here, is the quantum phase modulo 2. That's cool. I mean, here's this piece of aluminum living in a three-dimensional space, real space, and it's giving us the phase. Some people call this the Berry phase, and I showed this thing to Berry a long time ago, and then he did a whole bunch of stuff with the Berry phase that made him famous. That's where how many people have heard of the Berry phase? Just out of curiosity, I see a lot of things. Okay, well, there it is. It's gamma. Anyway, that is the way this works, and we've got a few more minutes here. I want to get this algebra out of the way before we go here to the thing. This general spin state has three real coordinates, and that is found by just doing the expectation values of these things that we're talking about here. So there's the rotation going on, but here are the actual components of that. They're polar coordinates, and when we use this for optical polarization, that is two-dimensional oscillators, which started this whole discussion, then what we're going to be seeing are two pictures. One, a real three-dimensional picture, which is this thing, but basically there's a spin vector sitting there, no sphere being shown now, just the polar angles, all with 2's on them. You see, there are 2's on every one of the angles here to indicate what has transpired in a 3D real space. Meanwhile, the angles without 2 are being shown over here for a polarization ellipse. So this is the connection between the U2 space, which involves complex numbers, two complex dimensions really, and the real space, which involves just three real ones. And that is a little bit more complicated picture there of the angles, the way they work. So these angles go with Stokes vector. This vector here, S, that means spin. In my opinion, it goes back to 1863, long before quantum mechanics. John Stokes invented Stokes vector. How many people have worked with a Stokes vector in any sort of way? So you will if you do keep in physics, because that's the way we're finding everything, by studying polarization very carefully. So this S really stands for John Stokes. That's a real three-dimensional vector, this guy, okay. And this angle here with a 2 on it, 2 times phi. Phi is the Faraday rotation angle. Michael Faraday gets into this. He discovered the rotation of polarization due to molecules that had some C-ness to them, some C, that curly stuff, okay. And then this angle right here, the aspect ratio of the ellipse, right here, this side, double that, and that's not a polar angle, it's an elevation angle of the spin vector. And then the nu is hiding in there as well. You turn this whole thing, that most people would call maybe that the Faraday angle. That's this angle, and you've got to go to C space to really see it as a polar angle. Okay, I think that's about all we need to cover today. That's enough. These are pictures that show those angles more clearly. And they show you also the actual behavior of this. So I'm going to end with this simulation right here. I'll leave this on this screen, and we'll go back, and the one that you saw coming in today, which is a rotation around the B axis. See the B crank up there, omega sticking out on the minus B side. That's in order to make it like we had. I'm going to go ahead and start that one going, just to give you a feel for what it is that it does. And I'm hoping the Stokes vector is showing. It isn't.
Pull it up under controls. Just swap out.
I'll just right click.
Sorry, the controls.
You've got to go control panel. Okay. Control panel. Click on
the Stokes and
right
deselect
here.
the cosine.
And
Deselect.
we'll get rid of this, right?
Yeah.
Okay. And let her rip. Where is it? Where is it? It didn't show. There's something else I've got to do.
Okay,
let's get normalized.
Leave the,
phasors out of
no,
No.
the print omega. This was changed this morning. This is exactly what
okay.
I tried to avoid.
So-
Go ahead and start that as is.
Okay.
As is.
Let's see if that gets this going here.
There we go. It's just occluded.
Okay, now let's get rid of it so it doesn't cover. Anyway, there's a spin vector going around, and here's this thing
That's what
going
the links
around.
were for.
Pardon?
The links would have been a little better, but
Yeah. I'll kill this and hope that we get the same thing that we said here. Okay, so let's just pause this thing. It started here, followed this, okay, and now it's almost, in fact it's pretty close. I hit right on, it's at the Y polarization point. Okay, it started out as X polarization. This is a really fast quarter wave plate, right? Instead of taking a million oscillations to get from X polarization to Y polarization, did it in about 4 steps. Okay, we've got a really big B coefficient here, okay, for bilateral rotation. And you can see what this thing has done. It's gone basically a quarter of a way, a little bit more. Now as it continues, okay, let's just continue this thing, resume, okay, we will come to a point where it's back home, so to speak, and I don't know if you saw that, I should have stopped it right there, that's where it was. Here you've got minus phase. It didn't return to there. You've got to go another rotation before it actually stops here. And you can see that in this plot. Let's let her go again. Resume, okay? When it peaks out again, whoop, I didn't catch it, but you saw it, it was right there, right? And now we've had a full beat, as measured by spin people. Now most engineers would tell you that beat frequency is always the difference of the two colliding oscillators, right? And I told you it was the half difference, and that's true. If you see here, this isn't quite the same beat as this one. This is the same, okay? I'll leave it run the rest of the way just to have it go through another beat to see that. But it's this kind of business that you're doing here, and you can see the spin vector starting off. We started off with A, and then we got to minus A, and then finally we get back to plus A. But it takes 2 beats to do that in a quantum mechanical system. The engineers are right for classical system, but not quantum. So it's some of the mysteries of these factors of 2 and all sorts of other things that we need to still discuss, and that will be the topic of our Wednesday lecture coming up in a day. And we're working hard to get all of the graphics so that it's foolproof.
We worked to the last minute, didn't we?
Yeah, yeah. Okay, any questions or?
And remember, always slow these suckers down. The best way to slow this thing down here is to go ahead and reduce the exponent.
Trying to hop over one.
Well, I should say make it more negative. There's one. That's pretty good right there, but go ahead and make it, that stops it. That's, oh my gosh, I'm doing the coefficient, aren't I?
Yeah, you could see it from an angle. I tried to hint, it was a
Yeah.
mantis instead of the
This is the guy that you need to reduce, just by one. And it creeps now,
You can't
right? Gives you
reset.
plenty of time to see what's going on.
Restart it to 0.
Yeah,
And then by the time everybody leaves, there'll be another beat.
yeah, this, I will simply reset 0, there we go. So we started with everything in this oscillator, and this one is just getting to be woke up. And then it now has that much of an amplitude, as you can see there, negative amplitude. And remember, phi over 2, okay?
That's not even running the new app.
Here, it catches the thing right here. Just as that one peaks out, that one's crossing the axis. The other way to think about it is, this is the one that's the receiver now. This one is the one that's has the phase ahead by 90 degrees. He's pulling him that way. Okay. Now he's pulling down. Now he's pulling. Just as he passes there, you want to have maximum amplitude over here. That's what pi over 2 really means. Get the force in sync with the velocity. Get F dot V to be max, and you're doing the best resonance you can with this linear resonance that we're talking about here. Now, we haven't talked about non-linear, so the laws are all different there. But we'll get to that soon enough. So I encourage you to work with this. This is, even in its current state, is a very useful program to understand things. Plus, I give some problems in it. You can check the problems.
That's not even the new version, Bill. Remember we had guidelines tracing the S, so you're working from an old copy.
Well, let's see if it,
Cache.
that new thing we put in there,
Yeah.
I put it on this computer.
The clear cache icon.
Yeah, I'm gonna just go ahead and pause it.
We've got different issues than a
This thing
normal
right here.
programmer would. Yeah.
You can look this up on any browser, but here we're just pushing it so we can click it. And then I need to go and control and get my Stokes vector going. And I'll leave that alone. I won't print that.
It'll only take 2 at a time right now anyways, because
Yeah,
there
let's see
wasn't
what
enough room.
happens. Reset t equals 0. Yeah, there we go. But I don't see the Stokes.
Disable the sign, the cosine like
Yeah,
I had that all configured in a link, and the link was labeled Stokes.
They should be radio buttons. That's one way to do it. Keep them distinct if you really want them to be distinct.
I was thinking
distinct,
drop
yeah.
down menu too,
Let's go ahead and do that. There we go.
and it's sized
Okay.
up, got
And now I'm
different
going to
labels.
take her down to slow. Just so you can see it. And there it is. They can just cross the axis. This thing is not quite maximum, right? It hits its maximum on the negative side. You got to do another lump here before you get it to hit the maximum on the positive side. So there's your extra -1 that comes in for the phase of the wave. The spinner, the spin vector doesn't care about that.
We need to have the twisting S head to really nail this down,
Yeah.
or S vectors spinning as it moves around. He's got that set up in another app called Color U2.
This guy right here.
It's really sharp.
Well, there's one old amp that's called Avoided that has all of it sort of, you just touch things and it moves, both the parameters and the variables. Remember that? You changed that.
I'll have to look it over
The
again.
avoided crossing. I mean, the avoided crossing is how ammonium maser got started, and it's part of the NMR story. I mean, it's a big deal. How you actually get excited two-level systems that come out of a beam, and then you've invented the laser if you have an appropriate resonator.
before them.
Back over again.
That was Charles Towns. That was long before. We really got an optical laser, but a microwave laser. It's called a maser. That was the beginning of the laser age, was the maser microwave. Yeah. It's the 24
Easier to work
gigahertz
with.
that is the tunneling frequency for an ammonia molecule. That's what he worked with. And it's called the ammonia maser when you actually use that. You know, it's a good way to get that
Do you know that
particular
wavelength?
24 jigs.
Did you say the wavelength size roughly?
24 gigahertz, it's on the order of 5 millimeters or something, 3 millimeters, something like that. It's very small. A gigahertz is light as a foot, right? Light goes a gigahertz in a foot. I mean, you know, a nanosecond.
I
Right?
heard someone else using that conversion once
Yeah.
online. It's,
You know, English, we're English, right? We're doing English stuff. We only get our metric drilled in when we have to. But yeah, that's kind of amazing too, because you know, here's the computer here, it's operating several gigahertz, right? So each of the little pulses in there, they're going this far in one clock cycle, in one fraction of a clock cycle, because it's more than gigahertz, right?
the orders of magnitude from your base.
Yeah. Yeah. Okay. Well, we'll take all this stuff to hell on Wednesday.